The model in this video is of a company that is planning to develop an e-commerce service. There is no marginal cost for providing the service, but a server facility must be constructed, which will require an upfront investment for each unit of annual capacity. The unit cost of capacity is assumed to be 80 cents, and the revenue per transaction is assumed to be $1. The new service is a fad expected to be popular for only 1 year. The transaction demand for the year of business is uncertain, but the company's best guess is a demand of 2 million transactions. Therefore, the company must decide how much capacity to build for this single year of business. If it builds more capacity than demand, the extra capacity will be wasted. If it builds less capacity than demand, it will lose potential sales. This model is a version of an important problem in management science and operations, usually called the news vendor problem. It is named after a news vendor who must decide each day how many newspapers to order in the face of uncertain demand. As in the current model, there is a cost of ordering too few and a cost of ordering too many. The best order quantity, or in this model, the best transaction capacity, must balance these costs. The logic of the model is very simple. Once an uncertain demand has been generated in cell C7, and a transaction capacity has been chosen in cell C10, the cost of capacity is 80 cents times the capacity, revenue is $1 times the minimum of capacity and demand, and profit is revenue minus cost. I've designated this as the only at-risk output cell. The transaction demand is assumed to be normally distributed with mean 2 million and standard deviation 500,000. Notice that at-risk's dice button is currently toggled to white, that is static. So the value you see in cell C7 is the mean demand, 2 million. With this demand, you might think it makes sense to use a transaction capacity of 2 million, as I've done here. With this capacity, which is equal to demand, the company makes a nice profit of 400,000. However, these values are misleading, and a closer look at the model reveals two important findings, one about simulation in general and one about news vendor models. First, the model as you see it here is essentially a deterministic model, where mean demand is used instead of a random demand. This is obviously unrealistic, but you might expect that the $400,000 is at least a good estimate of mean profit from a simulation model. However, this is not true, and it is often called the flaw of averages. To state this in more generality, when the means of uncertain inputs are substituted for the uncertain inputs in a simulation model, the resulting outputs based on these means are not necessarily equal to the means of the outputs in a real simulation model. Or to say it another way, best guesses for inputs do not necessarily lead to best guesses for outputs. The reason, at least in this model, is asymmetry. If I continue to use a 2 million capacity, but enter different demands by toggling the dice button to random and pressing the F9 key a few times, you can see what happens. If demand is greater than capacity, the profit remains at 400,000. In this case, the extra demand is lost, so revenue stays constant. But if demand is less than capacity, then revenue decreases, and so does profit. In fact, if demand is low enough, like you see here, profit becomes negative. So the largest possible profit is 400,000, and the actual profit can be considerably less. Therefore, the mean profit must be less than 400,000. To see how much less, I will run the simulation for 5,000 iterations to get a fairly precise estimate of mean profit. You might be surprised to see that the mean profit is nowhere near the $400,000 from the deterministic model. It is about half that value. This should be a very convincing argument for not using deterministic models when there is uncertainty, even when best guesses are used for uncertain inputs. The resulting estimates of outputs can be well off the mark. The second important finding concerns the best value of transaction capacity. You might think that a transaction capacity equal to mean demand, 2 million, makes a lot of sense. However, the cost of having too little capacity and the cost of having too much capacity are not equal. To see this, suppose that demand is fixed at 2 million. If capacity is 1,000 units too low, the cost is 200. I'll show that. $1,000 units too low, profit decreased by 200. This is because $800 is saved in capacity cost, but $1,000 is lost in revenue. So the net is 200. On the other hand, if capacity is 1,000 too high, cost is $800. This is $800 below the 400,000. This is because there is an extra $800 capacity cost and no extra revenue. This suggests that capacity should be low rather than high. I will use a risk sim table function to analyze different capacities from 1.2 million to 2.2 million. These values are actually listed in row 10 but have been painted white. I'll unpaint them. Then I will add a risk sim table referencing these values. And I will change the number of simulations to 6. And I will run the simulation. Here is a quick summary of the resulting profit distributions. In terms of mean profit, it looks like the third one down, 1.6 million, is best. Again, this is because the cost of having capacity too high is greater than the cost of having it too low. I can actually go a little further. If you have ever studied the news vendor model in a management science or operations class, you might remember the critical fractile for finding the best value of the decision variable, in this case, the capacity. It is the cost of being too low divided by the cost of being too low plus the cost of being too high. I will calculate it right here. It is 200 divided by the sum of 200 plus 800, or 20%. According to the theory, the capacity should be set to this percentile of the demand distribution, which can be found easily with at-risk's defined distributions tool. So I'll set the percentile to 20%. And I see that the value is about close to 1.6 million, as we saw before, a little less. And I can see that the resulting percentile is a little less than 1.6 million. That's the capacity that should be used.